suppose, let me first discuss one simple method. Suppose if we have, so I have this, so let me once again consider the simplest 3 by 3 case, A11, A12, A13, A21, A22, A23, A31, A32, A33 times x1, x2, x3. These are the formula. V1, V2. Now I can multiply this matrix with a lower triangular matrix. What is my aim? I want to choose my lower triangular matrix such that when I multiply this matrix with my lower triangular matrix, I must, so the idea is something like this. I am going to have a matrix which is 1, 0, 0, L21, 1, 0, L31, L31, 0, 1, like this. So I have only the first column. These are 1 and this is the first column. This is a lower triangular matrix. And then I multiply this one with A11, A12, A13, A21, A22, A23, A31, A32, A33. What will I get? I will get a matrix. The first row is same, A11, A12, A13. Now what will be the second? Second is L21 times A11 plus A21. Okay? Similarly, L21 times A12 plus A22. And L21 times A13 plus A23. Okay. Similarly, I will get L31 A11 plus A31. L31 A1 A12 plus A32. L31 plus A13. L31 A13 plus A33. So this is what I will get. Now I choose my L21 and L1, L31 such that in this matrix these two are 0. Okay, that means I want this to be 0. I want this to be 0. So I can choose L21 is equal to minus A21 divided by A11 and L31 is equal to minus A31 divided by A11. If I choose these two factors here, the resulting matrix is going to be, it is 0 and 0 here. I am going to have some elements here. Okay. So I am going to have some alpha. So everything I will call it as alpha. But it is only that alpha 1, 2, alpha 1, 3, alpha 2, 2, alpha 2, 3, alpha 3, 3, alpha 3. So this is going to be that, where these are exactly alpha 1 is same as A11, alpha 1 is same as A12, alpha 1 is same as A13. So I am transforming this matrix by an appropriate lower triangular matrix to a matrix where the two elements in the lower to this first column are 0, net 0.
That 3, 2 element need not be 0. in lower triangle matrix?
Yeah, it need not be 0, but even if it is 0, we can call it lower triangular matrix. There is no restriction that you should have everything non-zero. Okay, so now I am going to choose another lower triangular matrix and multiply with this. That lower triangular matrix is going to be something like this: 1, 0, 0. This also I am going to take 0, 1. I will call this as L3, 2, 0, 1. So in this case, you see I am taking them also to be 0. And I am going to multiply this with alpha 1, 1, alpha 1, 2, alpha 1, 3, 0, 0, alpha 2, 2, alpha 2, 3, alpha 3, 2, alpha 3. So what I will get if I use this, I will get alpha 1, 1, alpha 1, 2, alpha 1, 3, and this is going to be 0, alpha 2, 2, alpha 2, 3. There is no change in this. Now what about this? This one is 0 because this will multiply 0, 0 here, and this one is going to be alpha 2, 2 plus L3, 2 into alpha 2, 2. Okay, that is going to be this. And then the third part, this is going to be alpha 2, 3 plus L3, 2, well, L3, 2 into alpha 3, 3. So this is going to be my matrix. Now I am going to choose this L3, 2 by demanding that this element has to be equal to 0. So I want to demand that this is equal to 0, which means I must now choose my L3, 2. L3, 2 is equal to minus alpha 2, 2. Sorry, I think it is L3, 2 comes here. So when I do this, it is this. When I do this, L3, 2 into 2, 3 to alpha 3, 2. L2, 3, L2, 2 into alpha 3 plus alpha. So I am going to define this as alpha 3, 2 divided by alpha 2, 2. If I choose it like this is going to be equal to 0. Correct? So now I am going to have this is 0 and this is going to be some quantity which is different from alpha c. So let me call it as beta 3. So I have now converted by these two operations. This matrix has become an upper triangular matrix. Actually, you can do this even to find the determinant. After we get this matrix, the determinant is going to be product of these three. Okay, this is called triangularization of a matrix. By these operations, you actually triangulate the matrix. Okay, so once you have this triangularization matrix, so I have taken this matrix, I multiplied, so I will call this matrix as L1, I will call this matrix as L2. So essentially, I got this matrix from this matrix by multiplying L1 and then multiplying L2. So I must do the same thing here. I must first multiply this with L1, then multiply this with L2. So right hand side is also going to change. Correct? So let us say that so I will call all these things. So let me finally write the upper triangular matrix in the following fashion. Let us say this L1 and then L2 is going to give me U11, U12, U13, 0, U22, U23, 0, 0, U23. This is going to be my upper triangular matrix, and so you have L1, L2, operating on B1, B2, B3. Let us call this as G1, G2, G3. So what I have to now find is this equation: U11, U12, U13, 0, U22, U23, 0, 0, U33 on x1, x2, x3 is equal to G1, G2, G3. Okay, so algorithmically doing this kind of a transformation is a very easy job, because even if you have an n by n matrix, all that I have to do is I have to do this. I use the do loop and then do it. Take first column and take all the n minus 1 rows, make them 0. Take second column, n minus 2, make it 0. Take third column, n minus 3, make it 0. And go on doing that. So I will have at best n columns, and each column there will be diminishing number of rows to which I have to make 0. So this can be easily done on a computer. So now once you have this, the solution is simple. You know that if you look at the last row is given by U33 into x3 is equal to G2. So from here we can obtain x3 is equal to G3 by U3. Remember, I know this, I know this. I have to find out this. So first I will get x3. Then U22 x2 plus U23 x3 is equal to G2. But I already know x3. So I can write x2 as G2 minus U23 x3 divided by U22. Okay, I already know x3, so I can use that x3 to find x2. Now I know x3 and x2, so I can write U11 x1 plus U12 x2 plus U13 x3 is equal to G1. So my x1 is nothing but G1 minus U12 x2 minus U13 x3 divided by U1. So I can find out x1, x2, x3 from this upper triangular matrix structure. So this procedure of finding out solutions of an algebraic equation is known as Gaussian elimination. So Gaussian elimination method uses eliminating all this, converting a given matrix into an upper triangular matrix, and after the upper triangular matrix, this is called back substitution method. You first find out x2, substitute x2 get x1, substitute x3 and x2 to get x1 and so on. So this is called back substitution. If you have a lower triangular matrix, then you do a forward substitution. You first find x1, then get x2 from x1, and x1, x2 you get x3 and so on. So this is called Gaussian elimination, and this is very, very famous. It's used very much in the computers, solving linear equations on a computer.
Is it the same as LU decomposition?
LU decomposition is slightly different. LU decomposition, there are two methods. This matrix itself will be written as LU, the lower triangular matrix into an upper triangular matrix. So yesterday I indicated that LU decomposition so you can write down a matrix as the product of lower and upper triangular matrices. So that when you write LU into x is equal to B, you can write UX is equal to some G. I do not know this G. So first solve LG is equal to B by forward substitution. And then you will get G from here. Okay, from here get G. And then this G is known. Then UX is equal to B, you solve by backward substitution. then from there you get x. This is what you do in LU decomposition. Now if your matrix is a positive matrix, as we defined in the morning, some positive matrices, that means if matrix has no negative eigenvalues, then you can show that it is A can be written as L dagger if A is positive. Okay, this is called Cholesky decomposition. Cholesky decomposition is allowed for positive matrices. So A can be written as L dagger. Well, there is only one point which is computationally important. If you are working on a computer, there is one technical point that you have to keep in mind. That is, when you are trying to do this triangularization of the matrix, you have a problem. The problem is that if you have a matrix, you should not always think that you should do the second, third, and fourth of the first column. I will make them 0, because as you can see here, this A11 is in the denominator. But in your matrix, if A11 is a very small number, something like 10 power minus 5, let's say, then this becomes a very large number. And because of that, your matrix becomes the condition number of matrix becomes bad. So you will get a lot of errors because of that. So there is something called pivoting. So pivoting has to be done if you are doing this on a computer. What is pivoting is essentially you find out along the first column whichever number that is reasonably large. So first you transfer that row to the first row by a transformation. You can make a row transformation. So you can change the matrix by transforming the row corresponding to the element in the first column to the largest, and then put that in the first row, and then do the Gaussian elimination. So that is called pivoting. So pivoting is important when you implement it on a computer. If you don't do pivoting, sometimes errors can be very, very large. You may completely get results that are not at all physical, not at all the solutions to problems. So you have to keep this in mind. So pivoting. Okay, so these are some methods that we have for solving simultaneous